everyone, and thank you very much for allowing me to present my work here today. It's a very nice event, and I'm really proud to be part of it. So I'm going to tell you about work I've been doing following my PhD thesis in Grenoble here with Alexandre Foray. Now I moved in postdoc with working with Edgar Roldan in Trieste, Italy, in ICTP. So Edgar Roldan is mainly in the quantitative life science section of the laboratory. So I'm now a bit trying, to merge both sides of this research. So I come from, of course, a quantum thermodynamical background, and I'm trying to merge it a little bit with like quantitative life science that they do there. So especially there, they're like expert on martingale theory and first passage time. So I'm going to show you a little bit the connection that can be drawn between this and quantum thermodynamics. So today I'm going to tell you about a lazy quantum measurement engine. So to introduce you a little bit why I wanted to look at this in the first place, the motivation to me was that we all know that measurements, it brings information. So you have this famous thought experiment, the Maxwell-Diamond thought experiment, the Szilard engine. And why information is interesting is because we all know it's physical. So from information, you can lower the entropy of the system. And from this, then you have a spontaneous return to the initial state of your system. And if you're clever enough and you manage it well, then you can extract work from this. So we know that from measurement plus some feedback, we can have energy extraction. But in the quantum world, we have one additional key ingredient. So we have what we call back action. So back action basically is just the idea that when you measure the state of a quantum system, then it's going to change its state. If you do it, under some condition, of course. And here, since we're here to talk about energy, yes, so this was, yes. So it has some energetic consequences. So if the measurement observable commutes with the Hamiltonian of your system, then still you can have some interesting effects. So for instance, what you can have is that if I measure here, for instance, the state plus, so okay, for those who are not familiar, this is a Bloch sphere, and here I'm taking the convention of putting the ground state here and the excited state on top there. And this is my Hamiltonian, so my quantization axis for the energy is this one, and for the moment I'm measuring also in this basis, so just a projective measurement. So if I measure this state, I have some possibility of finding it in this excited state here, so it has more energy than initially, and if I end up there, then I have less energy than initially. So this change of energy from this plus state to this ground or this excited state is called quantum heat because of its stochastic nature. So it's a bit like when you interact with a thermal bath. You have, sometimes you gain, sometimes you lose, and it's stochastic. You cannot predict if you're going to gain or lose with this projective measurement. But here, on average, the total energy, if you repeat many measurements on this plus state, is going to be the same. So on average, after many repetitions, I'm going to end up with a state here, in this case, which has exactly the same average energy as my initial state. So we can do something a bit more interesting. We can do a measurement, so measure an operator which does not commute with the Hamiltonian of our system. So here I keep the same Hamiltonian for the system, but I'm going to measure here in this basis, so in the plus-minus basis. So if I do this, for instance, starting from the ground state, here you see, no matter the result I obtain, I'm always going to get more energy. So here, even on average, I increase the energy of my system. So it's nice now because we have, with quantum measurements, two aspects to measurements. We gain in energy and we can gain information, of course, as in classical systems. So from this, we can build quantum measurement engines. So to give you some example, this one I will be quick because I will tell you about a bit more later. But here you have 2 qubits. It's just a 2-stroke engine, and you have 2 baths like that. So here the idea is that you're going to measure your 2 qubits in a basis in which the basis state have some entanglement between the 2 qubits, and then this will allow you, for instance, to take energy from the cold reservoir and to put it in the hot reservoir. So that's one interesting thing you can do with quantum measurement engine. There is also this example. It's a quite recent paper from Etienne Jussieu and the group of Andrew Jordan, in which the idea is to start from also 2 qubits which are entangled in the ground state. So it also allows you to do a cycle, and in this case, you do local measurement and you can extract some work. Maybe you know of this result. So it's a work by Cyril Éloire and Andrew Jordan, in which you can lift a weight against gravity, or you can recharge a battery thanks to measurements. So here you're really using measurement back action and measurement information. For instance, what you would do is that you have a detector here, and if you find that the particle is in this region, okay, then it's the unlucky scenario and you do nothing. So this is your feedback, quite simple. But if you measure the position of your particle and that it's not in this region, then you can lift the plate without any cost and repeat again. And thanks to this, you can lift your weight as much as you want, so give some potential energy to your system at apparently, with the cost, of course, being paid by the measurement itself. So measurement plus information processing. And lastly, there is this paper, maybe you know of it, in which there are these 2 qubits, which starts, so importantly in this paper, we have 2 different splitting for the 2 qubits. We start with an excited qubit, which is the one with the lesser splitting, and the other one which is in the ground state. We couple them together, and then we measure one of them in its local energy eigenbasis. And thanks to this also, we can move the excitation that was in this lower energy qubit to this higher splitting qubit. So that's also one way to extract energy from the measurement. Okay, so now you know a little bit about quantum measurement in genes. I want to tell you about one additional one, because it will be interesting for this talk especially. So it is inspired by this work of, again, Cyril Éloire and in the team of Benjamin Huard, Alexia Ofez, and David Herrera-Marti. So in this case, I like it a lot because it's one of the most simple quantum measurement engine you can have. So here it's just a single qubit, and you measure it a single time per cycle. It can hardly be easier than this. So here the idea is that you start from this plus theta. So it's basically just this plus state that you rotate a little bit here. So you start from this state, and you measure it in the plus-minus basis. So in this case, as you see, you're going to give it energy on average, as I told you before. Not as much as if it was starting here, but at least you give it a little. So here you have some probability of reaching this plus state or this minus state. So keep in mind that what I call PG is the probability of jumping. So basically, if the angle here is quite small, it is the probability of significantly changing the state of my system. So this is the first step. So we do the measurement, which gives energy to our system. Then what we do is a feedback. So if we ended up in this minus state, we just do a rotation to break in back in plus. So this doesn't cost anything because, the energy of our system is just like given by a Hamiltonian, which is proportional to sigma z. So here we can do a rotation in the equatorial plane. It doesn't cost anything to us. And if it's in plus, we just remain in plus. So the goal is that at the end of this feedback step, no matter what the measurement outcome, we end up in this plus state here. Then we do some work extraction. So to do this, we couple the qubits to an electromagnetic field. So in our case, we'll consider that the electromagnetic field is big enough that it's classical, so that it will not, we neglect all entanglement between the qubit and the classical field. And so the idea is that when we connect our qubit to this classical field, there is going to be Rabi oscillation, an exchange of energy between the classical field and the qubit. And if the qubits start in this plus state here and that it evolves like that, then you see the qubit is losing some energy, which automatically goes in the field. So our goal is to amplify this classical electromagnetic field. So this classical field acts as a battery in our case. This is our goal, to amplify it. Okay, so in each case here, we're going to gain this work. So we're going to amplify the classical field by this amount of work at each cycle. And then, of course, we need to do the resetting of the daemons memory, which will be related to the probability PG and PR that we have here. Okay, so in this case, it's a little bit trivial, because since we have the feedback, then every cycle is exactly the same. Every cycle, we extract the same amount of work, and so we can just look at the cumulative work, which is just a linear function like that, which is very simple. So this is what we obtain. Of course, this is only like the work extracted. If we take into account the cost of the measurement, then it will be a similar curve, but just with like a little bit below, like that, because we have to include the cost of the measurement, of the information, sorry. Okay, so this was the introduction, a bit the context. Now I'm going to tell you the question I had in mind when starting this project. So I was asking myself, so this was a goal, let's say, basically. So can quantum measurement engine work without information processing? Because in this example I showed you, it's a little bit, I mean, we can be a bit sad about this cost of the information processing. Because most of the time, we are going to measure the plus state, but we still have to pay a cost for removing the information in the classical memory we used for the feedback. But sometimes, most of the time, it's useless because we know that it's very likely that we're always going to measure plus because it's much more likely to remain in the same place in the block sphere. Just to show you, yeah, it's much, this PR is much more likely than this PG. So most of the time, we're just going to do like this. But still, we're going to have to pay for the erasure of the information of the feedback, which most of the time is useless. So it's a bit frustrating. So we were wondering, okay, can we remove this information processing? Would we gain if we do this? So here is the outline of the rest of the talk, and I'm going to, if you want to know more, here is the archive link for like the paper this is based on. So first, yes, if you want to know, quantum measurement engine can work without information processing, and I will tell you how. But it's not always as simple. I mean, sometimes, in some cases, for some engines, you cannot work without information processing. So the best you can do is just to lower a little bit the amount of information processing you're using. So I will tell you how to optimize on this amount of information processing you're using. Then I will tell you about first passage time distribution in the context of quantum measurement engine. And lastly, I will conclude this talk. So quantum measurement engine without information processing. So very quickly, yes, it's possible, especially if you have thermalization. So in this case, you have a quantum measurement engine, but no information is used at all. So you just do the measurement, but you don't look at the outcomes. You don't care about the outcome. And since you don't care, you don't have to reset anything. You don't have to pay for a lambda-hour erasure in this case. But here it works fine because for each cycle, you're going to reconnect each of your qubits to its thermal bus. So it's fine. I mean, you don't have like interconnection between the cycles. There is a resetting in itself just because of the thermalization. The issue is that sometimes, for instance, with this example I showed you before with a single qubit, here we never thermalize the qubit. So here, if we don't do this feedback, what is going to happen is that our cycles are going to be interconnected together. Because if I don't want to do the feedback, if I'm not using the information, the state of my system, I don't control it anymore. It can drift after cycle, so this is a potential issue. So here, if I remove the cycle, what it means is that I'm always going to assume that I obtain the plus state. So if I indeed obtain the plus state, it's good, I'm going to extract some work. But if I did not, I'm going still to apply the work extraction step. But in this case, instead of extracting work, I'm going to take work from the battery. So it's bad because, of course, I'm lowering the energy of the battery, which is the opposite of what I want to do. So what is going to happen in this case is that, so this is the evolution of the work you give to your battery at every time step. And as you see here, on average, it goes to 0 with a number of cycle t. So what you see here, so in color is like several realizations. So here, as the cycles are interconnected, you see you have many different trajectories that are possible. And in black here, you see the average cumulative work that you extracted. So here you see very quickly it saturates. So what it tells you is that, because you started in this very favorable plus state, you can extract some work in the beginning, but then your state becomes equally distributed between this plus and minus, and then you cannot extract anymore. So it's not so interesting. So what we've done is to introduce a probability, a laziness probability. So we do the feedback as before, but we don't do it always. There is a probability to do it or not to do it. So this is going to impact, of course, the work we extract. And what we see is that the cumulative work we obtain is non-Markovian. Actually, it's second-order Markovian. So it's a little bit tricky to deal with it and to see the dynamic, but to be short, what we were very excited about is that actually the dynamic of the amount of work we extract, the cumulative work, and the state of the qubit follows exactly a run and tumble dynamic, which is used to model self-propelled particle motion. So this is basically the way all the probability works together, but maybe it's not so useful for you. So then what we can do is to look at the power optimization. So here, this is the average work we extract. So it's related to, the work we extract minus the cost of the information, which is just given by this quantity. So actually, it's not so simple to come up with this, but I can tell you more if you want. So the average power is simply this in the steady state divided by the duration of our cycle, which is simply proportional to this angle theta. And then what we have is the optimal laziness like that. So now what we can do is for the different parameter, and here what is very interesting to compare is like this h bar omega and the kBt, so like the quantum scale and this more or less classical scale. So for each of these set of parameters, we're going to have a curve for the optimal laziness depending on the angle theta. So if I do this with respect to this ratio here, so we call it a quantum to classical ratio, we obtain the following. So you see that when R is small, then we are classical dominated, so it's quite expensive to use this information. And when we're quantum, R goes to infinity. So here you see the optimal laziness depending on this quantum to classical parameter for different value of the angle theta. So when theta is very small, then it means that we're more or less in the zero regime, we're measuring very, very quickly. When theta is large, then it is the opposite. So here you see that when R is quite small, then it means that information costs a lot, so like the A ratio will cost you a lot. So it's better to be lazy. It's better not to use too much information because it costs you a lot compared to what you gain. And in the quantum case, it is the opposite. So information is key, so you still need to process it, but still, some laziness can be useful, even in this quantum case. So that's one message. So here, maybe just 1 minute on the stopping condition. So maybe you know that in statistical physics, people sometimes look at like particle like moving like that. It can be Brownian particle or active particles. And they look at when is the first time they're going to reach a given condition. So sometime on the position. In our case, we're going to look at it regarding like how much it will take for us to reach a given value of the work extracted. So this is what we call the first passage time. And just to be short, here we have a plot of the different first passage time depending on this probability to be lazy. So here, this is just to tell you that it's good to be lazy because then you have more power if you optimize it correctly. But at the same time, you lose a little bit because you lose, of course, in predictability of your engine. You see here that if you're quite lazy, you have this curve there. And so it tells you that if you want to reach a certain quantity of work extracted, you basically have to wait on average for an infinite number of cycles to be sure that all your trajectory have reached this given quantity. So there is also a trade-off, in the predictability of your engine. And in conclusion, just to conclude and to sum up what I've told you, quantum measurement engine where information is not, it's possible to have a quantum measurement engine in which information processing is not necessary, but we can also use a probabilistic back-action engine with a probability to use information or not, which can provide more energy in the steady state if you're a little bit lazy, but it leads to less predictability, and what is quite nice is that it can be mapped to a run and tumble process. So with this, I just want to acknowledge my coworker, of course, Debraj Das, with whom I've done this work, and Edgar Roldan at ICGP. If you have questions, comments, you can, of course, send me an email. So thank you very much for your attention.
Thank you, Léa. First question here.
Thank you, Léa. Maybe can you a bit comment on the thing, or I really don't see the difference, but what is the difference between laziness and your error? So, it's known that if you have a measurement error, so which basically your measurement apparatus has a readout error, is also lazy in principle. What is the difference to your
So-
setup?
As I would say, two different. I mean, first, here, it's true that it could be used to model some errors, but first, not all errors, because here it's only an error that you think you're in the plus state, but actually you were in minus. We don't have the opposite error. So it doesn't model like all the possible error you could have, and here it's very biased in one direction. So I wouldn't say it's a very good model for error because it's very much biased. And also here, the point is to optimize on it. So, I mean, if you have some measurement error in your process, typically you cannot change it. You have it, and maybe it's optimal, maybe it's not. Here we tell you, okay, you can do it on purpose to have some laziness in order to be more efficient in the power you get. So that's also a reason.
Hello. Yes, here. Thank you for your talk. I have two short questions. At some point, you mentioned that the process was non-Markovian.
Yes.
How did you estimate non-Markovianity? Did you calculate some specific measures?
So in this case, it's quite simple because we can explicitly see like on what depends the cumulative work at some given time t, and we see that the cumulative work at some given time t depends on the previous one and the before previous.
Okay, so you did not calculate some non-Markovian measures with distances and so on. It was just due to the
but
form.
I don't think we need to because it's analytic enough that we see directly from the equation. We see that it depends on the previous and the before last term. Yes.
Okay, thank you. And second question, it's more so at the beginning, but you can stay here with that drawing because you said, okay, most of the time it's probable that it will be close to plus. So in fact, there is no need to measure.
Yes.
But I think it depends. It should depend on the time.
On the angle, of course.
You need because if you, I think this limit where you stay close to plus, it's maybe close to the zero limit, where you will or.
Well, even if you have, like, for instance, in this drawing, here, even in this drawing, you see the probability to come in plus is much bigger than to go in minus. It doesn't need to be like order of magnitude. But even if it's just like you have 2-3 times more probability to go in plus than in minus, still, I mean, it's suboptimal to use the information every time. Yeah. So you don't have to have a very small theta, small angle here. It's even more true in this case, but even with this scenario with like a rather big theta, still it's much more likely to go in plus, and even that you can optimize a little bit on it.
Okay, thank you.
Thanks a lot. I had just two experimentalist questions. Like, how do you perform a projective measurement in the plus-minus basis? That's my first.
So I think that, I mean, what I've heard from Benjamin and Loire typically is that what they would do is to rotate the state in excited round, then measure, then rotate again.
But when you pay the rabbit unit for half a turn of the sphere, then...
Well, first it depends how you rotate it, because if you put the plus in the ground state, then you measure it. I mean, well, yeah, it depends how you do it, I think.
Okay, well, we can discuss that afterwards.
Yes.
I'm interested. Thank you.